Electromagnetic energy. What is light? Light is not matter because it does not have mass. Light is energy. Isaac Newton thought that light was streams of tiny particles traveling at high speeds that obeyed his laws of motion, whereas others, Huygens, Young, and Maxwell, showed that light was composed of waves. So, is light particles or is it composed of waves? Well, light turns out to be composed of both particles and waves. Light is another word for light, another term for it is called electromagnetic radiation. So electromagnetic radiation is a form of energy that's composed of perpendicular oscillating waves. One of the waves is an electric field, and perpendicular to that is a magnetic field. All electromagnetic waves move through space at the same constant speed, which is what we call the speed of light. So the speed of light is a constant, and all light always travels at that speed. It doesn't go faster or slower. All light always travels at the same speed. And so we will see that there are other forms of electromagnetic radiation, like radio waves and X-rays and other things that you might be familiar with that we could also technically call light because they're forms of electromagnetic radiation. And they all have waves that move at the same speed, or particles that move at the same speed, the speed of light. So this is a picture of what an a wave of electromagnetic radiation looks like. So the electric field would oscillate up and down on the vertical axis, going up and down. That's what an oscillation means. Oscillation means up and then down, and then up and then down, like an oscillating fan goes back and forth, back and forth. And perpendicular to the electrical component is a magnetic component, this one here, that's in the plane that it's hard to draw two-dimensionally, but this plane here goes straight out in front of the screen. So this wave is going to go out in front of the screen, and then it goes back behind the screen, and then in front of your screen, and then behind your screen. So the electrical component and the magnetic component move together. As one goes up, the other goes out. As the electrical goes down, then the magnetic goes in, and they always kind of move like this. So let's take a look at this video. So here's a visualization of what's happening when an electromagnetic wave propagates through space. So you can see the red component is the electrical component. Move closer, no. The red component is the electrical component. It goes up and down. The 0 point here is the line right in the middle. It goes below the line, and then above the line, and then down below the line. And you can see that every time the red component goes up, like that, then the blue component goes out. And every time the red component goes down, then the blue component goes back to the right. So they kind of do this dance where the blue one goes back and forth like this at the same time that the red one goes up and down like this. So this is just kind of an idea, to give you an idea of what electromagnetic radiation is composed of. It's composed of electric waves and magnetic waves. Electromagnetic. Radiation just means that it moves in a straight line. So when you turn on a light bulb, the light is emitted in straight lines from that light bulb in all directions. So it's radiating from the light bulb. So light travels at a speed 3 × 10⁸ meters per second, and sound is another form of energy. So energy, remember, is just things moving. So in the case of light, the things that are moving are electromagnetic waves, and in the case of sound, the things that are moving are waves in the air. So the air particles themselves kind of move up and down like the waves in the water, except instead of being composed of water molecules, they're composed of air particles. And those waves in the air we call sound waves. Sound waves can move at 340 meters per second. Light waves move much faster. So you've experienced this when you see lightning. You can see lightning and the light gets to your eyes very quickly because light travels very fast, and the sound takes much longer to get to your ears. You see the lightning before you hear it because sound travels more slowly. So when we think about a wave is just an oscillation above and below a baseline. It has certain properties like amplitude and wavelength. And when we think about amplitude, we're talking about how bright the light is. And when we talk about wavelength, we're talking about what color the light is. And here's what we think of visually when we think of amplitude. Amplitude is how tall the wave gets, how tall it gets when it goes up, and how tall it gets when it goes down. And wavelength is the distance in between two peaks. So you can imagine that I could decrease the wavelength here and have a wave that had a shorter wavelength and still had the same amplitude, where the waves would still go up as high, but they would maybe, go up and down much more often. And we can also imagine here some wave that had the same wavelength, the same distance between peaks, but one where the amplitude was higher. So the wave would go up like this, and then down like this, and up like this. So amplitude and wavelength. Amplitude is how bright a light is. Wavelength is what color a light is. Another property of a wave is its frequency. And frequency is the number of waves that pass some point in a given period of time. So if we're counting waves at the ocean, and we count how many waves crash on the shore in a minute, then you're calculating the frequency of those waves, how often the waves pass a point, and the point would be the beach. We can do the same thing when we think about a light wave. When the light, if we pick some point in space and count how many times the waves go by, the waves being these components here, if we count the waves, then we can calculate the frequency. So I pick this point in space, the waves are moving through space, and I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, figure out how many waves pass this point in space as the wave moves. And that's what we call the frequency. So the units of frequency are hertz, and what a hertz is per second. So if 10 waves, this would be a really busy beach, really busy ocean. If 10 waves crash on the beach every second, then I would say that the frequency is 10 hertz, or 10 per second. When you see to the -1, that means 1 over s, and we would say that per second. So 1 hertz equals 1 per second. 1 hertz, 1 per second. And we might be talking about ocean waves or light waves, or we can measure the how often your engine spins. We call that revolutions per minute. That's a frequency also, but we could measure it in hertz, how many times it spins per second. The total energy is proportional to the amplitude of the waves and the frequency. So different light waves have different amounts of energy, and that energy is proportional to how tall the waves are. Brighter light has more energy than dim light, and also the frequency. The color of the light has to do with its energy. For waves traveling at the same speed, the shorter the wavelength, the more frequently they pass. So we can say that wavelength and frequency are inversely proportional. As one gets smaller, the other gets bigger. When wavelength gets smaller, the frequency gets bigger. When wavelength gets longer, the frequency gets, as the wavelength gets longer, the frequency goes down. So wavelength goes up, frequency goes down. So this means that the wavelength and frequency are inversely proportional, and we can represent that mathematically by saying that the frequency is equal to the speed of light divided by the wavelength. So here's some more representations of waves. We can say that this wave has the longest wavelength. So from peak to peak, this is a long wavelength. If we look at the wavelength of yellow here, peak to peak, the wavelength of yellow is shorter. And peak to peak here, the wavelength of blue is even shorter. So we can see the visual representation of waves of different wavelength. These all have the same amplitude. This seems to go above and below the line by the same amount that this one goes above and below the line, and by the same amount as this one goes above and below the line. So all of these waves have the same amplitude, but they have different wavelength. And remember, wavelength is what color they are. So a wave with a long wavelength might be red, and a wave with a shorter wavelength than that might be yellow, and one with an even shorter wavelength than that might be blue. So if you know the colors of the rainbow, the colors in terms of increasing wavelength, or excuse me, decreasing wavelength from longest to shortest, go in order of the colors of the rainbow: red, orange, yellow, green, blue, violet. Red has the longest wavelength, and violet has the shortest wavelength. So here we can see that red, orange, yellow, green, blue, violet. Red is the longest at 750 nanometers, and violet is the shortest wave at 400 nanometers. So, and remember that distance, nanometers, that's the length in between two peaks of the wave. So, excuse me, you can see here, this is called the electromagnetic spectrum. And I said before that light, what we call light, we see light generally as being white light from the sun. But remember that the sun is actually made up of these colors. White light from the sun is actually made up of a rainbow, and you can see that when it rains and the sun's out. The rain breaks the sun's light into a rainbow, and we can see that that white light from the sun has red, orange, yellow, green, blue, and violet light inside of it. So the white light is composed of all of these colors. Well, turns out that there's even more light than that. So these colors are kind of hidden inside of the white light. Well, there's colors that have an even shorter wavelength than violet. So the wavelength gets shorter and shorter and shorter and shorter, and we get to violet. Well, there's wavelengths that are even shorter than violet. We call those ultraviolet. So those ultraviolet waves, and you've maybe heard of those before, those are the ones from the sun that give you a sunburn, UV rays. UV rays are light. It's just like the light that we can see, but we can't see it. So it has a shorter wavelength than visible light, ultraviolet light does, and our eyes are not tuned to that wavelength, so we're not capable of seeing ultraviolet light. And as we go this way and the wavelength gets longer and longer and longer, we get to red with the longest visible wavelength, and then with waves that are even longer than red, there's a kind of light called infrared. So you can see that infrared borders the red side of the visible spectrum, and ultraviolet borders the violet side of the visible spectrum. Infrared is another kind of light that our eyes cannot see, but it's still considered light because it's just electromagnetic radiation, and the only difference between the light that we can see and all of these kinds of light that we can't see is the wavelength or the frequency, which are just two ways of representing the same characteristic, which is how long the wave is. So radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, gamma rays, those are all electromagnetic radiation. They're all what we could call them light. They're just different in how long the waves are. So when we think of radio waves, the waves in radio waves are very long waves. The waves in visible light are shorter waves. And the waves in gamma ray, X-ray, when we get up here, These waves are very, very short. So the only difference between radio and visible and gamma ray is how long the wavelength is, the distance between peaks. It's the only difference between these types of light.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So here's an image of what an infrared camera might see. So, you know, a visible light camera would obviously just be a picture of this image. So you'd see a man with his dogs here. But if we take that same image and instead of using a visible light camera, we use an infrared light camera, the image would look like this. Because an infrared light camera, infrared is often associated with heat. So this man, it looks like this man is wearing shorts because his legs down here seem to be warmer than the part up here. So if he's wearing clothes, then we can't see the heat from his body because the heat from his body is being absorbed by his clothes, and his clothes are emitting less heat, so that would appear to be yellow here. But his legs and his face are warm, they're exposed, and so we can see the heat, the body heat being emitted. We can see this dog here must be a short-haired dog because you can see his heat is just like this man who has exposed legs. But this dog here must have a very thick coat because this man's sweatshirt is yellow, indicating that it's emitting some amount of heat, but this dog's coat is blue, indicating that it's not emitting very much heat at all. His legs are emitting very little heat as well. So this dog must have very short hair, and this dog must have very long hair. And this dog maybe has medium hair. You can see their eyes and their ears emit more heat than the rest of their body. The photoelectric effect describes what happens when light is shined on certain metals, light of certain wavelengths. So when Albert Einstein was doing experiments to try to understand the nature of light, he would shine light on different metals in a system like this one, where this electrode here is the negative side and this electrode here would be the positive side, and if they are connected, they'll generate a current, and we can measure the current down here on this current meter. So right now there's no wire going between them and they're not connected, so there shouldn't be a current. Well, Einstein found that if you shine certain light on the metal here, then suddenly there is a current, even though there's still not a wire. So somehow the light was causing this junction to be bridged, this gap was being bridged, so that something was coming from here to cause a current to be measured, a voltage. He tried to use different colors of light and different brightnesses of light, bright light and dim light, to try to figure out what it was that was causing this phenomenon, because it didn't happen with certain light. It wasn't every kind of light would cause this phenomenon. He had to use certain kinds of light that would suddenly make this happen, and other kinds of light wouldn't work. So he determined that it was not about how bright or dim the light was. It was not about the amplitude of the wave. Remember how tall it gets. It was more about the color of the wave. So very dim light of the right color would make this happen, but very, very bright light of the wrong color, and this still would not happen. So it didn't matter if it was bright or dim. It mattered if it was the right color. And so it had more to do with the wavelength than with the amplitude. So what Einstein gathered from this experiment was that he determined that light behaves like, although it does seem to have some properties like waves, it also behaves like a particle. So his explanation was that whether a wave is dim or bright has to do with how many photons are coming at a given time. So if you have very dim red light, then you have only a few photons of that wavelength. But if you have very bright red light, then you have a lot of photons at that wavelength. So the amplitude has to do with how many photons there are. But the wavelength has to do with how much energy that particle has. So Einstein found that as he varied the wavelength, he changed the color of the light, he could eventually knock those electrons free. And when he knocked the electrons free, they would complete the circuit and he would measure a current. So he found that the energy has to do with the wavelength. So energy equals the speed of light divided by the wavelength multiplied by this constant, the Planck constant. So because we also know that we saw earlier that the frequency is equal to the speed of light divided by the wavelength of an electromagnetic wave, that the energy has something to do with the wavelength. The energy was inversely proportional to the wavelength, like Einstein discovered. And because of the properties of waves, that meant that the energy was also proportional to the frequency. So one photon that's ejected at that frequency, so as soon as we hit the right wavelength, then the electrons will be ejected from the surface. And when we reach that wavelength, then we have found what's called the binding energy of that metal. So electrons are on the surface of the metal, and if we use a light with enough energy, then the photon can come in and knock the electron off of the surface of the metal. So electrons are stuck down here on the metal, and electrons are negative. And if we shine a light, and a light is made of these particles called photons, so if we shine a light with a photon that has enough energy, then the photon will hit one of these electrons, will knock into one of these electrons, and it will send the electron off of the surface of the metal. We can knock the electrons off by shining light on a metal. So when we find what color light does this, then we can measure the binding energy. Energy equals the speed of light times Planck's constant divided by this wavelength here. So if the metal is struck with light that has a shorter wavelength, so that means light that has even more energy, then the electron will get knocked off. It will still be able to escape, but now the electron has even more energy than the binding energy. So let's say that we need 1 unit of energy in order to knock the electron free, and that's red light. Well, purple light has more energy than red light, so if I use purple light, it has 2 units of energy. It has a shorter wavelength, 2 units for example, and so the purple light will also knock the electron free, but now the electron will be going faster. So with that purple light, once the electron is free, the free electron moves faster because it has 2 units of energy. So this is an example of the photoelectric effect. The kinetic energy of an electron is equal to the energy of the photon, so that purple one, minus the binding energy of the metal, and the binding energy we said was 1 unit. So the kinetic energy that this electron would have here would be 1 unit of kinetic energy, because it used 1 unit of binding energy to knock that electron off. 1 unit, use this epsilon. So think about this for a minute. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? No electrons would be ejected. Electrons would be ejected and they would have the same kinetic energy as those ejected by yellow light. Electrons would be ejected and they would have greater kinetic energy than those ejected by yellow light. Electrons would be ejected and they would have lower kinetic energy than those ejected by yellow light. So what do we need to know here? Remember, the energy is associated with the wavelength. So what we need to know is, does ultraviolet light have greater or have a shorter or a longer wavelength than yellow light? So here's yellow light with a wavelength of about 600 nanometers, and here's ultraviolet light that has a wavelength that is generally about 400 nanometers and lower. So anything that's lower than 400 nanometers will be ultraviolet. So ultraviolet has a shorter wavelength than yellow, which means it has a higher frequency, which means it has more energy. So if ultraviolet light has more energy than yellow light, then the electron would be ejected, and it would have greater kinetic energy. Because that extra energy, we would overcome the binding energy of the electron, and any extra energy that the photon has would be converted to the kinetic energy of the electron, so it would go faster. Kinetic energy is how fast the electron goes when it's ejected. All right, let's try another one. Which photon has more energy, a red photon or a purple photon? So again, we have to consult this table. A red photon has a wavelength of between 750 and, let's say, 675 or so. Those all look about red. And purple is down here at about 425. That's when purple starts. So we can see that purple has a shorter wavelength than red. So the way that wavelength and frequency and energy are related is that as the wavelength goes down, when the wavelength is shorter, the energy is higher. Short wavelengths have high energy. So gamma ray, their wavelength is very, very short, 10 to the minus 15 meters, incredibly short wavelength. They have the most energy. Gamma rays are very high energy. On the other side, radio waves are a very long wavelength, 10 to the 5. That means there's 10,000 meters is the wavelength of some radio waves. 10,000 meters. That's longer than mountains, it was saying. So very long waves, very low energy. Very short waves, very high energy. Very long waves, very low frequency. Long wave, high wavelength, small frequency. Small wavelength, big frequency. So look, frequency and energy go together. Large frequency, large energy. Low energy, low frequency. But wavelength is the opposite. As wavelength gets smaller, these other two get bigger. As wavelength gets bigger, these other two get smaller. So, to answer the question, which photon has more energy? A purple photon does. A purple photon has shorter wavelength, higher frequency, higher energy. What is the frequency of a photon with a wavelength of 750 nanometers? So frequency is this symbol. It looks like a V, but it's actually, we call that nu. And this symbol looks like an upside down Y. We call that lambda. So this is nu, and this is lambda. And nu is the frequency, and lambda is the wavelength. So, what is the frequency of a photon with a wavelength of 750 nanometers? So I don't have quite the right equation up here, except I can combine these two equations to give myself the right one. So we saw this in an earlier slide. The frequency is equal to the speed of light over lambda. And we can see that here. E equals h times v, or E equals h times c over lambda. So v equals c over lambda. They're the same. So that's what we need here. Or excuse me, not v, nu. Nu equals c over lambda. So nu, what is the frequency of a photon with the wavelength of 750 nanometers? So c is the speed of light. 2.99 times 10 to the 8th meters per second. And lambda is the wavelength. The wavelength is 750 nanometers. But wait, I can't actually leave this as nanometers, because remember, whenever I'm trying to put numbers with units into an equation, those units have to cancel. And I can't cancel nanometers and meters like this, because they're not the same unit. N, M, and M aren't the same unit. So I can't have those two units, and I can't put both of those numbers into this equation because my units would not cancel. So in order for me to use these numbers, I have to convert 750 nanometers to 750 meters. So how do I do that? Well, let's remember what nano means. Remember, these letters that come before, they mean they're prefix multipliers. They're associated with some number. So remember, kilo equals 10 to the third, 1,000. Oops. Little m is milli. Milli equals 10 to the minus third, 1/1000th. Well, n, nano, equals 10 to the minus 9. So it's actually really easy to convert 750 nanometers to meters. How do I do it? 750 nanometers is 750 times 10 to the minus 9 meters, because n equals 10 to the minus 9. So nm equals 10 to the minus 9m. So whenever you're trying to convert from nanometers to meters, you have to add this times 10 to the minus 9 in there. 750 nano meter. And now my meters will cancel. But if I didn't add this factor of 10 to the minus 9, my answer, my number, would be much, much different. So now that I have converted these units and I've put them into a form where they will cancel, meters cancels meters, now I can plug this into the calculator. 2.99 times 10 to the 8th divided by 750 times 10 to the minus 9th. So my frequency equals 3.9866 times 10 to the 14. And what is the unit? Well, after m and m are canceled, the only thing I have left is this per second, right? Over second. So this per second is also, remember, what we call hertz. Hertz equals over s equals s to the minus 1. Those all mean the same thing, per second. Per second, per second, per second. All right, last one. A nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. What color is the laser? What type of electromagnetic radiation? And how many photons does the laser pulse contain? So we can answer this first one pretty easy. What color is the laser? 337 nanometers. So nanometers, 337, that's going to be something below violet. It's going to be less than violet down here, right? 337 would be here. And this is ultraviolet. So that 337 nanometers is going to exist somewhere down here. Right, this would be 350. This would be, change the color here, 300. So 337 is going to be right about here, 337 nanometers. And this whole region here is ultraviolet. So what color is the laser? I can only say what color something is if it's within this visible region. Things that have this wavelength are red, orange, yellow, green, blue, purple. I can't say that anything here has a color. Ultraviolet is ultraviolet. All of these are the color ultraviolet. All of these wavelengths are the color X-ray. All of these are the color gamma ray. Our eyes have this special function where we can see different wavelengths as different colors. But there's no such thing, to us anyway, in ultraviolet and X-ray and gamma ray. We can just say that what color is it? Well, it's within the region of ultraviolet. All right, so type of EM radiation is ultraviolet, UV. How many photons does the laser pulse contain? All right, so in order to answer this question, we have to use this piece of information here, that the laser pulse contains 3.83 millijoules of energy. So when we think about how much energy a photon has, there's two ways that we can think about it. We can think about the energy that is associated with the wavelength. And there's also an energy, and remember the wavelength is the difference between waves that have a long wavelength and waves that have a short wavelength. Right? So there's an energy difference between these waves, and we can calculate that using this equation. There's also an energy difference that has to do with sorry, I'm concentrating trying to draw these waves. That has to do with amplitude. So these waves have the same wavelength from here to here, and from here to here. That distance is the same. So these waves have the same wavelength, but they have different amplitude. This wave gets really tall and goes down really far, really tall, really far down. This one doesn't go as tall. This one has more shallow peaks and valleys. So this one has higher energy. And this one has lower energy. This one has lower energy. And this one has higher energy. So we were talking earlier about the photoelectric effect and how bright light and dim light didn't have an effect, didn't seem to be a factor in determining whether an electron was ejected. It only had to do with this effect here, whether there was a short wavelength or a long wavelength, regardless of the amplitude. But it is true that waves that have a larger amplitude have more energy than waves that have a lower amplitude, because we think about each particle arriving, and as it hits a wall, and we turn on a flashlight, for example, over here. Turn on our flashlight, right? It shines, and what it's really doing is releasing photons. And those photons are going to strike this wall here, and that wall is going to turn red. This is a red flashlight, and so when I turn it on, the wall turns red. So these photons are coming out of the flashlight at the speed of light, and they have some energy, and every time a photon hits the wall, it leaves a little bit of energy. And the next one leaves, and it hits, and it leaves some energy. And the next one hits, and it leaves some energy. And the next one hits, and it leaves some energy, and so on and so on. Just like gas particles, when we talk about lots of gas particles in a container, and the gas particles are bouncing around in the container, and they hit the side of the wall, and as they hit the side of the wall, they impart pressure. And when we have more gas particles and more collisions hitting the wall at the same time, the pressure goes up. Well, when I have more photons hitting the wall at the same time, the color gets brighter. The amplitude goes up. It's the same color, but the color gets brighter. Well, if I have more and more photons hitting the wall, well, they're all leaving a little bit of energy. So higher amplitude is associated with higher energy, just higher energy over time. Right? One hits, it leaves a little bit of energy. The next one hits, it leaves a little bit of energy. The next one hits. So the more collisions there are, the more energy there is in terms of amplitude. So this is a bright laser, 3.83 millijoules. It has to do with how many photons there are. So we can calculate that. But in order to do that, we have to calculate what's the energy of one photon. Every time a photon hits the wall, and it leaves a little bit of energy, how much is a little bit? How much energy does each photon have when it hits the wall? If I know that, then I can say, well, how many photons are hitting the wall to give me this much energy? If I know how much how much energy each photon has, then I know how many photons I need to give me this much. That's what the question's asking. So the energy of a single photon has to do with its wavelength. Hc over wavelength. H is Planck's constant, 6.626 joule seconds. That's how we say this joule with the dot there, joule seconds. And I can't draw dots very well with this program, sorry. J dot S. Times the speed of light, 2.99 times 10 to the 8th meters per second, divided by the wavelength, 337 nanometers times 10 to the minus 9 nanometers. Okay, so let's make sure our units cancel, see what we'll be left with. Meters cancels meters. Second cancels per second. So what I'm left with is joules. So the energy of my photon is going to be in joules, which is good because this is an energy that I have here in millijoules. So let's plug this into the calculator. .626, oops, I forgot all of this in here. 6.626 EE negative 34 times 2.99 times 10 to the 8th divided by 337 times 10 to the negative 9th. So the energy of one single photon is 5.8788 times 10 to the negative 19 joules. So this is a very, very small number, 10 to the negative 19. So the energy of each photon hitting the wall is a very small amount of energy. So in order to get this amount of energy, there must be a lot of photons hitting the wall. So let's figure it out. Here I have 3.83 millijoule. And remember, milli is 10 to the minus joule times 5.8788 times 10 to the minus 19 joules. It's supposed to be an X here. Times 10 to the minus 19 joules per photon. Right? This is how much energy is associated with one photon. So 5.8788 times 10 to the minus 19 joules per photon in one photon. So, trying to change the color here, sorry. Joules cancels joules, and what I'm left with is a number of photons. My units will be photon. So divided I get 6.5148 times 10 to the 15 photons. So I had 3 sig figs here, 3 sig figs here. I should have 3 sig figs here. So that gives me 6.51 times 10 to the 15 photons. So that's a lot of photons to give me this much energy, but I would imagine that I would need a lot of photons to have a laser. Otherwise, a laser is a very, very bright light, right? If I have a very, very bright light, I need lots and lots of photons of that color to make a lot of energy to make the light very bright. So we can excite gas atoms by giving them electrical energy. When we do this, an element or a compound emits a unique series of photons and will make a light. So it's like turning on a light bulb. If I turn on a light bulb made of mercury, it looks blue. If I turn on a flashlight made of hydrogen, it looks pink. If I turn on a flashlight made of helium, it looks brighter pink. If I turn on a flashlight made of sodium, it looks orange. Or if I put sodium in fire, I burn it, it looks orange. If I burn potassium, it looks purple. If I burn lithium, it looks red. If I burn barium, it looks yellow. If I put barium in an electrical flashlight, it looks yellow. So if I give an element energy, it emits a certain color. If I give barium energy, whether it's electrical energy in a flashlight or fire energy from a flame, if I give it energy, it turns yellow. If I give lithium energy of any kind, it turns red. So giving elements energy, electrical or fire or heat energy, makes them emit light. When I put some element in here, potassium, makes the fire turn purple. I make that purple light pass through a prism, just like when white light from the sun passes through a prism and it makes a rainbow. When purple light from potassium passes through a prism, it makes a rainbow too, but the rainbow doesn't have all of the colors. White light from the sun has all of the colors, all the visible colors, red, orange, yellow, green, blue, violet. But purple light from potassium does not have all the colors of the rainbow. It only has purple, blue, light blue, and red. And in only these very specific wavelengths here. Every different element has a different series of a different rainbow. This is the rainbow from sunlight. Every single color is filled in. Red, orange, yellow, green, blue, purple. They're all filled in. But the rainbow, when I use the light from just barium, the rainbow only has these colors. When I use the light from just helium, the rainbow only has these colors. So these are called emission spectra. And this is an emission spectrum, and these are emission spectra. This is another emission spectra, a spectrum of oxygen, a spectrum of neon. Every element has its own spectrum. When I heat it up, I put it in fire, and I look at the light that it generates. They all have a different kind of light. They all make a different kind of rainbow. I can have an emission spectrum, which is when I heat an element up and it generates its own light, or I can have an absorption spectrum where I pass light through relaxed atoms and they absorb light. But either way, we can see that for Mercury, if I give Mercury energy, it's going to emit these wavelengths, these ones that are bright. But if I pass white light through relaxed Mercury, it absorbs the exact same photons of energy that it would emit. So the absorption spectrum and the emission spectrum are like mirror images of each other, because whether it's emitting or absorbing, it's the same exact energy levels, the same exact colors in both cases.